In this video, we're going to focus on the Fibonacci sequence and the golden ratio. So let's talk about the Fibonacci sequence first. The first term in the Fibonacci sequence is 0. The next term is 1. And each successive term is going to be the sum of the previous two terms. So Fn is going to be the sum of Fn minus 2 and F sub n minus 1, where n is equal to or greater than 2. So the first two numbers in the Fibonacci sequence are 0 and 1. To get the next number, you need to add these two numbers up. 0 plus 1 is 1. And then to get the next number, add the previous two numbers. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. 13 plus 21 is 34. 21 plus 34 is 55. 34 plus 55 is 89, and so forth. So you'll get these numbers as well. I'm going to stop at 377. So F sub 0 is 0. That's the first term. F sub 1 is the next term. F sub 5 is 5. This is F sub 10, which really is the 11th term, if you think about it, because F sub 5 is the 6th term. I just want to make sure that you know what these numbers represent. But now let's talk more about the Fibonacci sequence and the golden ratio. You might be wondering, what is the golden ratio? The golden ratio is the limit of the ratios of successive terms in the Fibonacci sequence. So if we take the third term and divide it by the second term, that is 1 divided by 1, we're going to get 1. If we take f sub 3 divided by f sub 2, or take the fourth term divided by the third term, that's going to be 2 over 1, which is 2. And then if we take 3 and divide it by the previous term, 2, we get 1.5. If we take 5 and divide it by 3, we're going to get, so let me get my calculator out for this one. So this is 1.6 repeated, or 1.667 if you round it. Next, let's take 13 and divide it by 8. Notice what these numbers approach. So this is going to be 1.625. And then if we take 21 divided by 13, that's going to be 1.61538. And then let's take 34 divided by 21. So that's going to be 1.619047. And then 55 divided by 34. This is going to be 1.61765 approximately. And then 89 divided by 55. So looking at, well, this is going to be 1.618 repeated. So looking at these numbers, as this sequence progresses, what is the ratio of the successive term by the previous term? Notice that it's approaching 1.618. If we try a few more, let's say if we take 144 and divide it by 89, you could see this pattern develop even further. This is going to be 1.617978. And then the next one, 233 divided by 144. This is 1.61805 repeated. So the golden ratio is approximately 1.618. That's not the exact answer, but it rounds to that value. So let's think about what this means. As n becomes sufficiently large, the Fibonacci sequence approaches or approximates a geometric sequence. So starting with the number 144, if we multiply 144 by 1.618, we can get 233. If you type in 144 times 1.618, it'll give you 232.992, which is approximately 233. And then if you take 233, multiply it by 1.618, you can get the next number. This would be 376.994, which rounds to 377. So if we take 377, multiply it by 1.618, we can approximate the next number in the Fibonacci sequence. And that is going to be 609.986, which is approximately 610. And you could confirm that. If you add the previous two numbers, 233 plus 377, it gives you 610. So the golden ratio helps us to get the next term in the sequence. Now you can also go backwards. If you take 233 and multiply it by 0.618, it'll give you 144. You'll get 143.994. Likewise, if you take 144, multiply by 0.618, it'll give you approximately the previous term when n is very large. This will give you 88.992, which rounds to 89. Now, if you try to use that for the smaller numbers here, it's not going to work very well. So when n is, let's say, greater than 12, then you could use the golden ratio to approximate the next term in the sequence. Now, where do we get these numbers, 0.618 and 1.618? Where do they come from? Here's the exact values of those two numbers. If you type in the square root of 5 and then add 1 to it and then divide by 2, you're going to get the first number, the larger one, which is 1.618033989. And then if you take the square root of 5 subtracted by 1 and divide by 2, you're going to get 0.61803398887. Now, later in this video, I'm going to talk about how you can actually get those exact values. But that's where the numbers come from. So that's the exact value of the golden ratio. So here's a question for you. We know that f sub 12 is 144. As we said before, this is f sub 0, f sub 1, f sub 2. This is f sub 6, f sub 10. So f sub 12 is 144. Knowing that, what is the value of f sub 20? How can you estimate f sub 20 or even calculate the exact value instead of just adding numbers in a sequence? Well, keep in mind, when n is very large, the Fibonacci sequence approaches a geometric sequence. So we could say that f sub 20 is approximately f sub 12 times the golden ratio. Since we're increasing, we're going to use the square root of 5 plus 1 divided by 2 raised to the 8th power, because 12 plus 8 is 20. We need to multiply f sub 12 by the golden ratio 8 times to get to f sub 20. So go ahead and type that in. So this is going to be 144 times For those of you who want a decimal value, this is 1.618033989 raised to the 8th power. So you should get 6764.935 approximately. So rounding that to the nearest whole number, this is 6465. So that's the 20th term in the sequence. Now let's check it to make sure that this is correct. If we add these two terms, 233 plus 377, we're going to get that number that we had before, which is 610. And then if we add 377 plus 610, that's 987. And then 610 plus 987, that's 1597. And then adding that to 987, that's 2584. And then 1597 plus 2584, that's 4181. And then 4181 times or plus 2584, that gives us 6765. This is F sub 14, F 17, and this is F 20. And so we can see that this answer is indeed correct. Now, it turns out that there's a formula where you can calculate the exact value of this number. And here it is. F sub n is equal to 1 plus the square root of 5 raised to the n power, and then it's minus 1 minus the square root of 5 raised to the n divided by 2 to the n times the square root of 5. So if we want to calculate f sub 20, it's going to be 1 plus the square root of 5 raised to the 20th power minus 1 minus the square root of 5 raised to the 20th power divided by 2 raised to the 20th power times the square root of 5. Now, you could use a scientific calculator to get the exact answer. But for those of you who don't have it, you may have to use some decimal numbers. So once you type it in correctly, you should get 6765. And it gives you the exact value. So we could try another one. Let's say if we want to calculate f sub 16, it's going to be 1 plus the square root of 5 raised to the 16 minus 1 minus the square root of 5 raised to the 16 divided by 2 raised to the 16 times the square root of 5. And you may want to put that in parentheses. And this is equal to 987, which is the number that we see here. So that's the formula that you could use to calculate any number in the Fibonacci sequence. Now, there's some other interesting things regarding this sequence that we could talk about. For instance, let's focus on this number, f sub 13. F sub 13 is between f sub 12 and f sub 14. In fact, f sub 13 is the geometric mean, or it's approximately, rather. It approximates the it's approximately the geometric mean between f12 and f14, since the Fibonacci sequence approximates a geometric sequence when n is large. So if you were to take the square root of 144, multiplied it by the square root of 377, this will give you 232.997. which is approximately 233, the middle number. So when n is large, the middle number approximates the geometric mean of the previous term and the successive term. You could try that with another number. For instance, if you take the square root of, let's say, 987, multiply it by the square root of 2584, you'll get 1596.9997, which is approximately 1597. Now let's talk about how we can derive the values of the golden ratio. This number 1.618 and the other number 0.618. We're going to start with this. F raised to the n is equal to f raised to the n minus 1 plus f raised to the n minus 2. Dividing both sides by f to the n, we're going to get 1, which is equal to f raised to the n minus 1 divided by f to the n. Whenever you divide, you need to subtract the exponents. So n minus 1 minus n, that's n minus 1 minus n, these cancel, you just get negative 1. So this is f to the negative 1. The same is true here. N minus 2 minus n will give us negative 2. So we get f raised to the negative 2. Now I'm going to multiply every term by f squared. So this is going to be f squared is equal to f to the negative 1 times f squared. You need to add the exponents. Negative 1 plus 2 is 1. So you get f to the first power. And negative 2 plus 2 is 0. So that gives you f raised to the 0 power. Anything raised to the 0 power is 1. So we have this. Moving f and 1 to the other side, we get f squared minus f minus 1 is equal to 0. Now let's talk about how we could derive the numbers that describe the golden ratio, 1.618 and 0.618. So we know that each number in the Fibonacci sequence is the sum of the previous two numbers. F sub n is going to be proportional to r to the n. The reason for that, when we had numbers like 55, 89, 144, 233, 377, if we multiply 144 by the golden ratio, which we'll call r, 1.618, it's going to give us the next number, 233. And if you multiply 233 by r, or 1.618, it'll give you approximately the next number. So we could say that f sub n is proportional to r to the n. And the previous term is going to be proportional to r raised to the n minus 1. And the previous term to that will be proportional to r raised to the n minus 2. So we're going to start with this equation. R to the n is equal to r to the n minus 1 plus r raised to the n minus 2. Now what we're going to do is we're going to divide each term by r raised to the n. So on the left, these two will cancel, giving us 1. Now r to the n minus 1 divided by r to the n, we need to subtract the exponents. N minus 1 minus n, the n's will cancel, giving us r to the negative 1. And dividing these two, we're going to get r to the minus 2. Now the next thing we're going to do is multiply everything by r squared. So r squared times 1 is just r squared. R squared times r to the negative 1, we need to add the exponents. Negative 1 plus 2 is 1. And then negative 2 plus 2 is 0. Anything raised to the 0 power is just 1. Now we're going to take the two terms on the right side and move it to the left side. So we're going to have r squared minus r minus 1 is equal to 0. And so what we have is an equation in quadratic form. So we're going to use the quadratic formula to get the answer. R is going to be negative b plus or minus the square root of b squared minus 4ac divided by 2a. And this is in the form ar squared plus br plus c. So we can see that a is 1, b, that's negative 1, and c is also negative 1. So it's negative, and then b is negative 1, plus or minus the square root of negative 1 squared minus 4. A is positive 1, c is negative 1, divided by 2 times 1. So these two negatives will cancel. That's going to become positive 1. Negative 1 squared is positive 1. And then we have negative 4 times negative 1, which is positive 4, divided by 2. So we're going to get 1 plus or minus 1 plus 4 is 5 divided by 2. And so thus we have the two values for the golden ratio. So we have 1 plus the square root of 5, or we could say the square root of 5 plus 1 divided by 2, which gives us 1.618, and then 1 minus the square root of 5. That's going to give us a negative number. Which is negative 0.618, which we really don't want that. What we do want is the square root of 5 minus 1 over 2, and that will give us 0.618. But at least you know how to get this number, and this one too, just the negative version of it. Now there is another way you can get this number from this number, and it's by taking the reciprocal of it. If you take 1 and divide it by 1.618, you're going to get 0.618. So if you were to take this number and put it under 1, here's how you can get the other number, or at least the exact value of the other number. So that's what we have right now. So first, let's multiply the top and the bottom by 2, so that these 2's will cancel. And we're going to get 2 divided by the square root of 5 plus 1. Our next step is to multiply the top and bottom by the conjugate of the denominator, which is the square root of 5 minus 1. So on the numerator, we're going to get 2 times the square root of 5 minus 1. And on the denominator, we need to FOIL. The square root of 5 times the square root of 5 is the square root of 25, which is 5. And then this is going to give us negative root 5, and then positive root 5. And then 1 times negative 1 is negative 1. The two middle terms will cancel. They will add up to 0, and then we'll have 5 minus 1, which is 4. So we have 2 times the square root of 5 minus 1 over 4. Now working towards the left, we can break down 4 into 2 times 2 and cancel a 2. And so this gives us the other number, the square root of 5 minus 1 over 2, which is 0.618. So those are some different ways in which you can get these two golden ratios, 1.618 and 0.618, or these two numbers. So that's it for this video. Hopefully it gave you some good information on the Fibonacci sequence and the golden ratio. Thanks for watching.